started right now. Thank you. Thank you, Omer, for reminding me to turn on YouTube. It is on now, and let me check whether it is up or not. Yeah, it should be up now on YouTube. There we go. And then Julian is typing, so I'm gonna wait until that is done. And the new topic for today is base conversion, and I'm just reminding myself here, what I need to go over. So first question is, do you want me to go over Tuesday's lab? I am not getting any responses. Okay, all right. Cool. All right. So, given that is my response, oh, thank you, that's very good. Given that is the response, I am not going to go over that lab. Doesn't mean that people cannot ask me questions, afterwards about that lab. All right, so instead of going over that, we can now get started with there are a few things too. So this is not needed. I do not require people to watch this particular video of how I test a circuit and how I grade some of the labs in using Logisim, but I think it will be quite useful if people want to understand the process by which I grade your submission. And this is a zip file containing the tool referenced in the video. And for those people who want to learn how to use the command line interface in Linux, because that's what I use. Okay, my computer is a Linux computer. Doesn't mean that you have to buy a new computer to install Linux. Okay, because all you can do, what you can do is to install Windows. Cannot remember what the S stands for. Windows subsystem for Linux or something like that. Basically, it's a virtual machine. WSL1. It was not a virtual machine. It is an emulation layer. And then WSL2 is actually a full-up virtual machine. You don't have to use WSL. You can use any type of virtual machine. So we got VMware, VirtualBox, QEMU, KVM, and so on. So you can use any virtual machine and just get a Linux system installed on it in order so that you can use the same scripts that I use for various things in this class. Otherwise, you can learn how to use Windows to do exactly the same thing. Windows can probably do everything that I do in this class that I'm doing in Linux. And if you install Cygwin, which spells as Cygwin, you might be able to use the bash scripts and whatnot. Okay, but if you really want 100% compatibility, just install Linux. It's free. Okay, so we got a few text messages here. Yeah, VirtualBox is pretty easy to set up, and it's also free. The free version of VirtualBox is quite capable already. Definitely enough for what we need in this class. All right, so VirtualBox for 400 as well. Okay, that's very good. Okay, so you have one single virtual machine, and it doesn't really take up a lot of processing resources, especially if you only need the command line interface and without a GUI. So that really does not take up a whole lot of resources. All right, so there is that. This is the lab for today. It is due at 1:20 p.m. today. I don't want anyone to be spending time to work on this because I am going to talk about the topic for today, which is values, numbers, and bases. So let's go there. All right, so this is about base conversion. Okay, I know some of you probably have some exposure to base conversion from other classes, and some of you may have no exposure whatsoever to base conversion. So we're going to start from scratch. Okay, we're going to talk about the concepts, the general idea of what is a value and what is a number and what is a base. Okay, so we'll talk about those general concepts first, and then we'll do some examples, and then we'll get into the itty-gritty details of what equation we can use to do this and what equation do we use to do that, and so on and so forth. All right, so I'm assuming that all of you have read this particular module because that is what I have recommended over and over again is to pre-read a module before a lecture. I mean, all the modules are already listed in the sequence that I will go over them. So once I finish a particular module, the next one is just whatever is on that list in Canvas. All right, but this one, I think it's relatively easy to understand. When we get to the equations, and the formulae, that might get a little bit technical, but I think in general it's not really that bad. All right, so I can do this in a few different ways. Let me use mousepad. Okay, so I'm just going to use mousepad, and we'll go ahead and open a new tab for today. So the first question is, do you know how to make change for, let's say, $19.75? So if you're working at McDonald's and the change is supposed to be $19.25, I know that's a really odd number as change, but let's just say that is the case. Do you know how to do it? So anyone who who wants to tell me or let me know that you don't understand that process, now would be a good time to tell me, because otherwise I'm going to assume that you already know how to make change. In US currency, okay, let me just add that little piece in US currency. We got a few people typing. Not exactly that. I want the change to be $19.75. I want to give the customer back $19.75. Someone bought something for a quarter and then give me a $20 bill. So I have to make a change of the worth of $19.75. All right, so Jonathan gave me the answer already, so does Kyle. Okay, so I'm going to assume that you guys know the process already, because nobody told me via the text channel nor direct message that this is not something that they already know. Okay, so we'll take a look at this process. So we have $19.75. So the question is, how do we know that, right? I mean, one other way to do this is really easy. We can give the customer 1,975 pennies. That will do the job, right? But that probably will get a person fired from McDonald's, because one, it's going to take a long time to come up with that many pennies, and two, the customer may not be very happy to have to haul away close to 2,000 pennies. That may not be the best way to do it, right? So we also have this hidden, usually not mentioned, criterion of, we want to use the least number of bills and coins. Okay, that's usually not spoken but understood. So in that case, we basically look at all the common denomination of US currency, and we say, do we have any $20 bills? Nope, we do not need any $20 bills. The next question is, do we need the next one down is a $10 bill? We go like, yeah, we can use one $10 bill. Okay, and after the one $10 bill, we move down to the $5 bills. Yep, we're gonna need one of those. So one $5 bill. I know there are $2 bills, but since they're not very common and people get confused and use it incorrectly, so we'll just kind of skip the $2 bill and go straight to $1 bill. We will need 4 of those $1 bills, right? So now that takes care of the $19, and we have the 75 cents left. Yes, I know we have half-dollar coins, but those are also very uncommon, so we'll skip that. We'll skip to quarters. So we look at 75 cents and go like, oh, okay, that's exactly 3 quarters. Okay, so 3 times quarters, and we're done. Okay, so this is how we do this. So most people, you know how to do this kind of through experience. Okay, so you have already done this many times, and you can check the change from the other party and so on and so forth. So you know this process already. If you know how to do this, you already know how to do base conversion. Now, if you're thinking in your head and go like, what does this have anything to do with base conversion? Well, that's because we have never looked at, well, I shouldn't say we, but most people have not looked at base conversion in this particular context. Okay, So let me propose. Okay, let me first point out, how convoluted, the U.S. currency denominations are. We start with a penny. The next one up is a nickel, and then the next one up is a dime, and then the next one up is a quarter. So as I said, we're going to skip the half dollar. So we'll go all the way to the $1 bill. We'll skip the $2 bill to the $5 bill, $10 bill, $20 bill, $50 bill, and so on. So for all practical purposes, this is enough, for most people, because a $50 bill is fairly uncommon that people would use. Okay, so now we look at the ratio between the adjacent denomination. So there's a 5x over here, right? To go from a penny to a dime, it's 5 times the worth of a penny. A dime is 2x the worth of a nickel. And over here we have some really kind of odd stuff here, right? I mean, a quarter is 2.5 times the worth of a penny. And now we have 4x, because a dollar has 4 quarters. So far we have not even recycled a particular ratio, okay? And then the next one up is 5x again. So people would think that we are now, going back to a cycle, 5x, and then this one is actually 2x. Great. Okay, so far so good. So the next one up is probably a 2.5x, because that way we are basically just recycling the pattern that we have already established. No, that is not the case, right? Because a $20 bill is 2x the worth of a $10 bill. The 2.5x goes here. There's no regularity whatsoever, okay? And yet, you know how to deal with this. Don't you find this fascinating? Okay? I find it fascinating, okay? I find it fascinating, especially for people who moved into the United States, when they're fairly grown up, okay? Because the currency system of different countries can be very different. So this is the currency system, or the denomination system that we use in the United States. So if I were a politician, I would propose something that is useful. So I'm going to change the currency system. I'm going to change the denominations. So how am I going to change it? I will have a dollar bill, so the unit is always going to be here. But in order to make this more systematic, the next one down as a coin is going to be half dollar. The next one down is going to be a quarter of a dollar, and I might even have a coin for an eighth of a dollar. On the other side, after $1 bill, I'm going to have a $2 bill, and then a $4 bill, and then an $8 bill, and then a $16 bill, and then a $32 bill, and then $64 bill, and so on. So what do you notice about my proposed denomination system? What do you see here as opposed to what is currently in use? What is the ratio between the adjacent denomination? Exactly, it's constant, right? Everything is just twice of whatever is before that. That makes it a very easy system to remember, okay? Because there's no such thing as sometimes it's 5, sometimes it's 2, sometimes it's 2.5, and then it's 4, and then it seems to repeat, but not really quite, okay? Nope, this is like uniform, it's always 2x, okay? So, under this new system, let's try to figure out how to make change for $19.75. Okay, so now we write it out again, $19.75. So we are going to look at $64 bills. Nope, don't need that. What about 32? Nope, don't need that. What about $16 bills? Yeah, we're going to need one of those. So after the $16 bill, after one $16 bill, we would have $3.75 left. So the next one down is 8. We don't need an $8 bill. Next one down is 4. We do not need a $4 bill. We do need a $2 bill. Am I the only one that saw 2 times x? 2 times x. Or is it 2 to the power? Oh, okay. Yeah, so we're going to get to that, okay? Very good observation, but we'll get to that, okay? So, but right now I'm just doing the same kind of math that most people do when this becomes the new denomination system. This is how people will do it. Yeah, yep, because we only have either 1 or 0 of a particular denomination. That sounds kind of interesting, right? And then after that, we need a $1 bill. And then after that, we need a $half coin. And then after that, we need a $quarter coin. And then after that, we need none of the $1/8 coins. There we go. Okay, so as many of you have noticed, each multiplication consists of a coefficient. I'm going to call this, a coefficient for now. Later on, there's another name for that. And then it's multiplied by a particular quantity, which always seems to be a power of 2. So in this case, we have 0 times 2, and I'm going to borrow the caret symbol here to mean to the power of. And we have to be super careful because in C and C++, the caret does not mean to the power of. Instead, it means exclusive OR, bitwise exclusive OR. So I'm just going to borrow it for the time being because that's kind of a standard for people who do not program in C or C++. So this is to the power of 5 and so on. So I'm way too lazy to manually copy everything. So I'm just going to copy and paste, and then I'm going to change the powers of 2. This is 2 to the power of 4, and this is 2 to the power of 3. So you probably notice that there's also a sequence to the whole thing because the powers of 2 are just going down 1 by 1. And then this is 2 to the power of 0. Then some people may say, oh, what are we going to do with the fractions? That's okay, not a problem. We just keep going, okay? Keep decreasing the power of 2. This is 2 to the power of -1. Exactly, Justin is exactly right. And this is 2 to the power of -2. And this one is 2 to the power of -3. Okay, because 0.125 is just 1/8, which is 1 divided by 8, which is 1 divided by 2 to the power of 3, which is also 2 to the power of -3. So I do make certain assumptions of the level of math that people understand up to this point in this class. I wish I could add a prerequisite to all of the computer science classes where algebra is a minimum requirement. But I think there might be some pushback because, well, some of my colleagues may not agree to that particular plan. All right, so we look at this, okay, and we go like, okay, so far all of these are base 10 numbers, okay, and somebody mentioned here that we are dealing with binary numbers, right? So where do we do the conversion to binary? Well, let's think about what a number really is. So I'm gonna put some question marks here, and to put some comments and say to do and say convert to base 2. Okay, so we're going to go back and deal with this later. Instead of doing this, I'm going to look at the base 10 number 19.75, and we say, what exactly does that mean? Okay, this is a number, right? But what value is being represented by this number? Well, the first question is, what base are we using? What base are we using? Okay, because it is just implicit. Okay, it's implicit that we're using base 10, but there's no reason why we have to use base 10. We could have been using base 11. We could have been using base 16, and so on. So the first thing we need to do is to say, yeah, unless we say otherwise, a number is in base 10. Okay, so if it is in base 10, that means 19.75 is 10 plus 9 plus 0.7 plus 0.05. Yeah. The only reason why we use base 10 is because we have, guess what, 10 digits, 10 fingers. Okay, because the word digit actually means finger. Okay, so we got 10 fingers. which is not a very good base to use. Okay, we like base 10 because we have been poisoned from elementary school to say, yeah, we should use base 10. That's just a convention. Okay, it's nothing more than a convention. There's no specific reason that base 10 is superior to other bases. I mean, really, there's no reason, no reason at all. We have been taught to use base 10, and so we now think that base 10 is quote unquote right, and all the other bases are awkward. Okay, no, I'm going to challenge that. All right, so we look at this and we go like, what is the other way to say 10? Maybe we can just say this is 1 times 10. You go like, wow, Tech, this is a college class. Why are we doing, math like this, right? This is 7.1, and this is 5 times 0.01, and all of these are in base 10, okay? Unless I specify otherwise, we're dealing with base 10 numbers. So do we have any questions or disagreement about this? No disagreement? Okay, very good. So now we move on and say, oh, guess what? 10 is actually 10 to the power of 1. And 1 is 10 to the power of 0. 0.1 is 10 to the power of -1. And 0.01 is 10 to the power of -2. Do you go like, yes, I can see a pattern here, because 10, 1, 0.1, and 0.01, those are all powers of 10, integral powers of 10, and they're all in decreasing order. So the bottom line here is when we look at a number, okay, when we say a number, it is a representation of a value. So there's a difference between what a number is and what a value is, because the same value can be represented by different means, okay? And this is just one alias to specify what we know, or what in base 10 what we call 19.75 or 19.75. But what each digit is doing is representing the quantity of a particular power of whatever base that we are using. So this 1 is representing how many 10 to the power of 1s do we have. This 9 here is telling us how many 10 to the power of 0s do we have, and so on. Are we good so far? Are we understanding this concept? Okay, very good. Excellent. Thank you for the confirmation. I taught this class as a summer class, and for whatever strange reason, maybe it's just because the class size was smaller, when I ask questions like, are we good? Do we need to explain this any further? It's like dead silence. Okay, it's almost like, just I'm a radar, and all my students are extremely advanced stealth planes. There's no return signal. There's nothing that I get. There's no ping whatsoever. Everything is just blank on my radar, despite my best effort to go like, okay, let me just crank up the radar signal, the pose. No return whatsoever. It's like dead silence. Yep. Oh, okay, so it's not just my summer class. Huh. That is interesting. I'm going to have to think about the theory to explain that after this class, obviously. Okay. No, I really don't know. I mean, that's just really strange. Zombies. Yeah. Summer zombies. Summer zombies with a Z. Yeah, that would be a nice movie title, right? My summer vacation. My summer class. The heat was too much. Yeah, movie title is Summer Class. There we go. Someone should take up that movie title and run with it. Anyway, getting back to this, okay? So, if I were to ask you, how do we represent 1 times 10 to the power of, I don't know, 5, okay? In base 10. then you go like, hey, we notice a pattern here, because it seems like, the number of digits, after a digit, to count down to the decimal point is the power of 10. Okay, that is represented by a particular digit. So to write out 1 times 10 to the power of 5, it would be just 1 followed by, guess what, 5 zeros. So the number of zeros is matching what power of the base we're dealing with here. Does that make sense? This is the convention. Okay, by the way, this is how a number is formatted. Okay, this is how a number is formatted. Okay, excellent. Thank you for the confirmation. So this gives me a little bit of a clue to go back to my original question here, because if I need to represent 2 to the power of 6, I can now just say that this is 0 times 1 followed by 6 zeros. 1, 2, 3, 4, 5, 6, but in base 2. So instead of using 10 to the power of 5, this is using 2 to the power of 6, because there are 6 zeros after the 1. Alright, so given this is the way we spell out convert to base 2, for each power of 2, then we can just go ahead and rewrite this in a particular way. Now I explain this portion in slightly different ways every semester, so there are no 2 semesters that I do this exactly the same way. Okay, so now this is 2 to the power of 5, which is 1 followed by 5 zeros in base 2. Okay, and now we have a 1 times 2 to the power 4, which is 1 followed by 4 zeros in base 2. So the base is determining what value should we use as the base when we are dealing with the power, and then the number of zeros after a particular digit is telling us what power are we dealing with. So here is a 0 times 2 to the power 3, which is 1000 in base 2, and I'm pretty sure you guys are going like, okay, this is going to get a little bit tedious because I still have a few more digits to deal with here, but that's okay, because this gives you some time to kind of think about this and go like, am I understanding what is going on here? Okay, what is being converted here? So this is in base 2. This is alright, so now we have another one down here. And this one is kind of interesting because it's 2 to the power of 0, which means there is no 0 after the digit. Okay? And the next one is even more interesting because this is 2 to the power of negative 1. What do we do? There are no zeros to the right hand side anymore. That's okay, because this is what the decimal point is intended for. The decimal point is a separator. Okay? It's a separator to separate the digit representing whatever base to the power of 0 from whatever base to the power of negative 1. This is the separator between the 0 and the negative 1. So in this case, we can now say, oh, okay, so that means this is 0.1 in base 2, and the next one up is also a 1, and this one is 0.01 in base 2, and then the next one up is a 0, and it is the quantity that it needs to be multiplied by is 0.001 in base 2, just like that. Now if you are thinking about, okay, I'm still not getting the negative power and how it is 0.1, 0.01, and 0.001, just look at the base 10 number. Okay, so just think about how you represent 1 times 10 to the power of negative 3 in base 10. Okay, this is represented as point, okay, because remember the point here is separating the quantity of 10 to the power of 0 from the quantity of 10 to the power of negative 1. We have no 10 to the power of negative 1, no 10 to the power of negative 2, 1 of 10 to the power of negative 3. So that means the first digit to the right hand side of the point, to the decimal point, is representing the quantity of 10 to the power of negative 1 when we are using base 10. But since we're using base 2 here, so this is representing the quantity, or this 1 is representing the quantity of 2 to the power of negative 1. So where the digit is from the decimal point, if we call this the first one, then it is 2 to the power of negative 1. If it is the second place, then it's 2 to the power of negative 2, and so on. Are we doing this? Okay, so Daria is confused. What is the confusion? So I need a little bit more clarification of what the confusion is. Which part is not understood? The base part. Well, okay. So what I want you guys to see is the pattern, okay? The pattern between what we already know how a base 10 number is represented. What is each digit doing? What is this 7 doing here? Okay, what is this digit of 7 doing here? Well, the placement or the position of this particular digit says the 7 is telling us a quantity of what, right? Well, the quantity or the unit is based on the position. So this particular digit, has a position of one place to the right hand side of the decimal point. So it is responsible to tell us how many 10 to the power of negative 1s do we have. What about the 5? Well, the 5 is right next to it. So this 5 is telling us the quantity of 10 to the power of negative 2. That is the convention. In other words, okay, let me make an abstraction out of this, but in base 10. Okay, so if I were to say, okay, let's just look at a pattern of a base 10 number. It is AB times AB dot CD. Okay, so A is a base 10 digit, B is a base 10 digit, and so on. So what is it representing? A is representing the quantity of 10 to the power of 1. B is representing the quantity of 10 to the power of 0. C is representing the quantity of 10 to the power of negative 1. And then D is representing the quantity of 10 to the power of negative 2. That is the convention. That's how we interpret a number in order to get to the value that the number is representing. Okay? But this is in base 10. So the only thing about base 10 is what base are we using when we are dealing with the powers. That is the base. Now, when we look at this example here, they are all converted to use 2 to the power of something. So the base is no longer 10, it is now 2. But what each digit is doing in a number based on its position is still the same. It's still following exactly the same rules. So that is why when we look at point 1 in base 2, we are asking, we are basically asking the question of what this 1 is representing. So the answer is based on its position being just one place to the right hand side of the decimal point. This digit is telling us the quantity of 2 to the power of negative 1. Why it is 2 to the power of negative 1? Why 2? Because that is the base of this number. Why to the power of negative 1? Because it is one place to the right hand side of the decimal point. So are we doing okay with this example? Does it still add up to 19.75? Well, I will let you guys tell me about it. So unless I did something stupid with my math, which wouldn't be the first time, we have 16 plus 2, which is 18. 18 plus 1 is 19. 19.5, and then we have 19.75. So unless in the process I did something not smart, that should be it. Alright, so my watch is telling me to take row right now. So let's go ahead and take row. I mean, you guys probably know that I was about to take row today because you saw row taking and there's a date of today. Nope, this is the wrong class. Never mind. But you saw this, right? Earlier, as much as I was trying to hide this from people, I think most of you saw this, okay, when I scrolled the window. So that's what we are going to do is to take row. It's not open yet, so let me show you the answer first, and then I will make this viewable to you, and then we can go answer that question. Alright, so the answer to the question is negation. I'm going to type it in the text channel, all lowercase, so this way you can just copy and paste it. Wow, I mean, that should be fairly easy. Okay, so I will give you guys close to 10 minutes to do this. So the window to do this is about 10 minutes. The quote-unquote quiz is going to end at 9:48. Save and publish. So if you refresh your Canvas page right now, you should be able to see the quiz, and you have the next 8 minutes to answer the question. I mean, this is something that should take you like 10 seconds to do. All right. And in my other window, I can actually take a look and see how many people have done it. Alright, so let me take a look at grades. Yep, that's how I take row in my class. I just pick a random time during the synchronous lecture, post something stupid like this and go like, okay, where did I choose for row taking purposes, and that's it. No, it's not set up for extra credit stuff, unfortunately. What about last? That's an interesting question. I think the person who did it last actually deserve a little bit of recognition too, because I guess you can call that person like to live dangerously. I'm not sure whether I should encourage people to live dangerously. Like, I'm gonna run my car all the way down to the last drop in the gas tank. Sometimes you don't have a choice and you have to do it, but other times may not be the best idea. Alright, so I see that most people are done with it. Yeah, that's an awesome sequence of movies. I used to have glasses, with thick frames like that. I'm not sure how many of you have done your MBTI test, the Myers-Briggs type indicator personality test. My type is INTP, and guess what my superpower is? INTPs have a superpower that most people do not have. We can kill something that most people cannot kill. You might be thinking, oh no, Taki's going to talk about something violent. Nope. No. No. Time. Yes, Ethan is correct. INTP's superpower is to kill time. And most people who know me agree and say, yeah, that's something that you can do better than anybody else. Anyway, okay, so I think we're done with the row taking stuff, and we're not going to get back to this example here because we are not done yet. It's called a MBTI personality test, and you can go to a site called 16 personalities CISP310.com. That's one place where you can take the personality type assessment. There are plenty other personality type assessments. They're really actually useful. Okay, humor aside, it's actually quite useful because I think these tests, as long as people answer the questions honestly, these tests can really help people understand their aptitude, what they are really good at, and also preferences. And understanding that can really help a lot when it comes down to what job to take, and so on and so forth. So I do encourage people to take their personality assessment if they have time. I mean, it's not going to take you a long time, maybe 20 minutes or something like that. Well, it depends on what your chip is telling you to do, right? Yeah, my vaccination shot, is planting a chip in me. Well, I have to say that chip may not be working. I think I need a refund because my chip is broken. Oh, that you're lucky, Matt. You got 5G, out of your chip. I got nothing out of my chip. It's just drawing power. Anyway, so we're going to look at this again, and we are going to say, so where's the number? I see an addition with a lot of terms, but where's my number? Okay, so let's go ahead and answer that particular question. Okay, so I'm going to do something lazy again, and just do a copy and paste. Now this part is recorded, so I would not just blindly copy whatever I have on the screen. Instead, I'll jot down concepts, ideas, and your own understanding in your own words. Okay, that is the importance of taking notes, is to help yourself reinforce your understanding of the concepts. Alright, so the first thing is, hey, that's just not a very good, smart way of doing this. So instead of doing this, I'm just going to say this digit is a 0. I do not have any 2 to the power of 6. Okay, so the next one is the same thing. So let me turn off insert mode so I can just do this. None of those. And this one we got 1. This one we got none again. Okay. And this one we also got none. This one we got 1. So I'll just go ahead and overwrite these two. We got 1. We got 1. We got 1. And we got none. Okay. So I have just done something to get rid of the 1 times, 0 times, and so on. So now we look at this addition. And even though we have not talked about binary addition, I think most people see this and go like, oh, okay, so for each column, we just line up everything and just say if there's a 1 in that column, there's a 1 in the answer. If there's no 1 whatsoever in that column, we just have a 0, as the result. So that would be the right way to look at this. So in this case, we would have none of the 2 to the power of 6, none of the 2 to the power of 5, 1 of the 2 to the power of 4, none of the 2 to the power of 3, none of the 2 to the power of 2, 1 of the 2 to the power of 1, 1 to the power 1 of the 2 to the power of 0, and here is my separator, because without the separator we don't know where the power of 0 is located. Now we know because the digit representing the quantity of 2, in this case to the power of 0, is the digit that is immediately to the left hand side of the point. We really should not be calling this the decimal point anymore because decimal implies base 10. This is now the binary point. So now we move on to 2 to the power of negative 1. Yes, we got one of those. 2 to the power of negative 2. Yep, we got one of those. And what about 2 to the power of negative 3? We got 0 of those. That is my binary number. Are there any questions right now about how we got? Okay, other than I did not align everything right. So there we go. Everything is now aligned right. No questions? Okay, so that's base conversion. Okay, I did use a very long way, scenic route to explain base conversion, but that really is base conversion. Now, I want to focus also on not just base conversion, but what is a number, okay? So, a number consists of a lot of digits, okay? So I'm going to use D0 to represent the digit representing the quantity of whatever base to the power of 0. To the left hand side is D1, which is the digit representing the quantity of whatever base to the power of 1. And then we have D2. In other words, things to the left hand side, they are the more significant digits. And then things to the right hand side are the less significant digits. So that means we now have a point here as a separator. Then we have D subscript -1, which is representing the quantity of whatever base to the power of -1. And then we have D -2, D -3. So these numbers, the -2, -3, and so on, they're supposed to be subscripts. But since I don't have the capability of doing subscripts using a regular text editor, they just look like this. So if this is in base B, so I'm even using a symbolic name for the base itself. Okay, so in this case, what is the value? So the value in this case is basically a summation. You can use the sigma term. I goes from, in this case, -3 to 2, and each term that I'm summing is going to be D whatever the subscript of I is times 2, times B, because we are using a symbolic name for the base, so times B to the power of the same I of the index. So in this specific case, because we only have 3 digits to the left hand side of the point, and we only have 3 digits to the right hand side of the point, so I can now limit the range of I from -3 to +2. Do we have any questions about this representation? We got some people typing in the text channel. I'm gonna wait a little bit. I'll let you guys have some time to digest this. Okay, no question. Okay, 51. Yep, okay, so all right, so I missed Vlad's question. What is the difference between 2, 5, and base 10? Well, it's just B. If B is 2, it is binary. If B is 10, we're dealing with base 10, which is our usual base. If B is 16, it is it's called hexadecimal in computer science. But B doesn't have to be one of those quote-unquote convenient values. Okay, 2 is great, 16 is great, 10 kind of it's okay. But B can also be something that really kind of is odd. Okay, so we'll talk about that. It's it determines it determines the base of the power. Okay, that each digit is representing. Octo is an odd one. Octo is not really used that much anymore because we have base 16, which is hexadecimal. So octo is great for certain things, but these days it's not really used that much, except for escaping unprintable characters using a backslash. So we do use octo sometimes, but typically we use hexadecimal these days, because you need more digits in octo compared to hexadecimal. All right, so I'm looking at the time. It is 9:52, so we got some more time. So what we have done so far, okay, let me go back to my notes here so that I can kind of relate to where we are currently at. Okay, so we have talked about all of these concepts, and this is a sigma notation. So let me just explain this, this particular expression here. This is for base 10. So D subscript whatever is the digit position. So 0 as a digit position is the digit that is immediately to the left hand side of the decimal point. D1 is the one digit that is to the left, immediately to the left of D0. D-1, on the other hand, is the digit that is immediately to the right-hand side of the decimal point, and so on. So assuming that a number has an infinite number of digits, which is possible, okay, you can assume that, because even for something that is relatively simple, like this particular number here, I could pad zeros indefinitely on the left hand side. So I can just keep padding zeros here. So you can kind of imagine that a number inherently has an infinite number of digits. It's just that most of them are zeros. And I can do the same thing to the right hand side of the last digit that I have written here, because you can also imagine that there's really just a whole bunch of zeros here, but those are all zeros. So this relates back to this equation here, because as an index, I can start with quote-unquote negative infinity as an integer, and it can go all the way to positive infinity, because what I is doing is it's really just saying, okay, let's focus on one single digit of this number, and it is at position I. What are we going to do with that? Well, we multiply that because it is representing the quantity of something. But what is that quote-unquote something? It is 10, in this case, to the power of I, because we're dealing with base 10. What if we are dealing with some other bases? Well, then the equation becomes like this. So b is just, a placeholder of whatever base we choose to use. All right? So now let's go ahead and take a look at some really kind of strange base that we probably do not want to use in general. So we're going to say, what about base 7? 7 is not just odd, it is prime. Well, so is 2. 2 is a prime number too, but base 7 is something that most people do not have experience with. That makes it a very good way or good example to use, because it really forces people to think about the concepts of what a number is and how do we convert a number, how do we understand the value represented by a number. So I'll give you a random example. Okay, this is not pre-planned. I'm just going to say 413 in base 7. What value is it representing? Then you go like, but Tech, we have never learned anything about base 7. That is true. But I have just taught you how to look at a number and find out what value it is representing. It is right here, which you are supposed to have read before class. Okay, so how do we use that? Well, we can say, so I'm going to spell out the summation here. I doesn't have to start with negative infinity because we don't even have decimal points. Okay, so in this case, we can say I start with 0, and the position of the digit to all the way to the left hand side is digit 2. So I goes from 0 to 2, and then each term that we are multiplying in this case would be d subscript I. So remember, the 3 here is d0, okay, because that's digit 0 representing the quantity of 7 to the power of 0 here. So this is multiplied by whatever base, because this time we have a constant of 7 as the base, to the power of I. Okay. So let's go ahead and expand this summation here. So we have 3 times 7 to the power of 0 plus 1 times 7 to the power of 1 plus 4 times 7 to the power of 2. Alright, so I'm just looking at the text channel. Okay, so I got one little thing I need to take care of first. There we go. Alright, so now back to here. Yep, so the digit that we can use for each base is 0 up to whatever the base is minus 1. Then you go like, well, that doesn't seem to make sense, right? Well, let me ask you this question then. Is there a single digit in base 10 that represents the quantity of 10 itself? The answer is no, because we only have 0 to 9 as single digits, right? So 10 as a quantity requires 2 digits, 1, 0, to represent the quantity of 10. Now, I know, from a certain perspective, that sounds really confusing, because most people equate the quantity of 10 automatically with the representation of 10 as a base 10 number. Okay, but when we think about the quantity or the value of 10, this is what we are talking about. This is why I turned on the webcam, because I need to show you the picture. Okay, show you what I'm displaying with my fingers right now. This is the quantity that we know as 10. Writing it out as 1, 0 is a representation of this quantity. Okay, it's just like what you're seeing here with the webcam. This is me. Okay, this is a person. Okay, this person turns out to be called Tak. Okay, so Tak is a way to refer to this person, but I can also be referred to by other people using different names. Okay, are we doing okay so far? Differentiating between what a value is versus what a number is, because I think it's extremely important to make that distinction in this class. Okay, very good. So I got a bunch of confirmation down there. All right, so now we can finish this calculation. 7 to the power of 0 is just 1, so it's 3 times 1. And we have 1 times 7, because 7 to the power of 1 is just 7. And then we have 4 times 49, because 7 to the power of 2 is 49. And now we just have to add it up. So 3 plus 7 plus, okay, this is 196. And then we just do the addition. It becomes 206 in base 10. So 413 as a base 7 number is what we know as 206. Are we good with this conversion? This is converting from quote-unquote base 10, base 7 to base 10. Okay, very good. What about the other way around? How do we convert from base 10, or a value that is already represented as in base 10, to a particular base? So let's look at 206 again in base 10. And I'm going to say, what about if I want to represent this as a base 5 number? What do we do? Let me point out a equation that is useful, but I wouldn't say it is super duper useful, but it's useful. Okay, so this is a equation that can go back. If you know the value, let me zoom in a little bit here. If you know the value v, okay, and you want to convert it into a base b representation, and you only want to know what is digit I, this is how we do it. Okay, now it only gives you one digit at a time, which is very tedious if you want to convert the whole number, but it gives you the foundation of doing base conversion for all the digits. So we'll take a look at this equation, memorize. And by the way, this symbol here that looks like a square bracket missing the top is called the floor function. So the floor of a value is the largest integer that is less than or equal to that particular value. And if you want to get a better explanation or longer explanation, just Google it. Just go ahead and find floor function in Google search and go to Wikipedia, and it explains not only the floor function but also the ceiling function. You don't need to read the entire thing, just the first portion is going to be fine. Okay, just read the first 2 paragraphs, and that explains what is the floor of a particular value. No, floor is not rounding up. It is not rounding. It is the largest value that is less than or equal to whatever you're taking the floor of. So I would not do any equating to rounding, because it is not rounding. It might look like rounding, but it's not. So okay, let me give you some examples. I'm gonna use a separate part here. Okay, so the floor, okay, so it might look like that because the floor of 2.6 is the largest integer that is less than or equal to 2.6. So we say, okay, that's just 2. The floor of 1.1 is 1 because 1 is the largest integer that is less than or equal to 1.1. That seems pretty simple. The floor of -2 is -2 itself because -2 is the largest integer that is less than or equal to -2. What about -1.1? That's right. That's why it is not rounding. It's not truncating, it is what it is. It is the floor is the largest integer that is less than or equal to whatever you're taking the floor of. Alright. So, but since we are not going to be dealing with the negative values, we can sort of use truncation in place of that. Alright, so let's go ahead and try to figure this out. Okay. So we want to figure out what is D0, which is the digit representing the number of 5 to the power of zeros. So that may sound kind of stupid, right? But we're going to apply the function. So we're taking the floor of 206. I'm not going to use the 10 in parentheses because it's understood that it is in base 10. And we want to divide it by 5, which is the base we're dealing with here, to the power of 0, which is, that's pretty stupid because 206 divided by 1 is just 256 mod 5. Okay, so that would give us a 1. What about D1? D1 is, okay, I'm just going to be a little lazy here, so I can just copy and paste the format and go ahead and change just a few things here. So this one is saying, let's divide it by 5 first, okay, and then we do the mod 5. So if you divide 206 by 5, you get what? And take the floor of that too. So you get 41, right? So you have 41. Let me see. Yeah, 41. So 41 mod 5 is also a 1. Alright? Because, okay, let me try to spell this out because just in case I did something wrong. So we have the floor of 206 divided by 5, the whole thing mod 5, right? So 206 divided by 5, so that's where the math is 41. So we have 41 mod 5, and the answer is 1. Now, for those people who are thinking, because I don't see any questions, what is mod? Well, you need to get back to your CISP310 material and figure out what is mod. Mod is the percent operator. Modulus, exactly. So if you don't remember what it is, look it up. Look it up. Alright, so what about the next digit? What is D2? Exactly, the remainder of integer division. Alright, so now we have this thing here. So this becomes the floor of 206 divided by 25. Take the floor of that and then do the mod. Alright, so what is 206 divided by 25? And take the floor of that. I believe that is just 8. So it becomes 8 mod 5. And the answer is a 3. There we go. And I think we're done because you can see how this particular value, oh, actually we are not done yet. We actually have a D3. So D3 is the floor of 206 divided by 5 to the power of 3, and then the whole thing mod 5. So that is the floor of 206 divided by 125. Yeah, so we have that digit being non-zero. So that is just 1 mod 5. 1 mod 5 is 1. And there we have it. We have our base 5 number. So if people are saying, I don't see a base 5 number, okay? Then I go like, well, what do you think D0, D1, D2, and D3 are representing? What is the 0, 1, 2, 3 doing as a quote-unquote suffix of the D. The 0, 1, 2, and 3 are the positions of those specific digits. D0 is the one that is immediately to the left-hand side of the decimal point, which in this case is not needed. And then D1 is the one to the left, and so on. So that means this really boils down to 206 in base 10 is 1311 as a base 5 number. The reason why I know there's a D3 is because this number here, this value, is greater than or equal to 5. So I know we have at least one more digit. And when that digit, when that value is less than 5 or less than whatever base we're using, then we know all the other digits that are more significant, they're all going to be zeros. How would you convert two bases with neither base being 10? I like that question. Alright, so let's give that a try, shall we? Because what you need to do is to understand how to do multiplication, subtraction, addition, and that sort of stuff in a different base. So let's go ahead and give it a try. So I'm just going to randomly pick something. So we'll go ahead and say 215 as a base 7 number, and we want to convert it into a base 5 number. Okay, so let's see if we can do this without going through base 10 first. Okay, so we're gonna have to use division. Okay, because all of these things they basically boil down to division. So the first thing we need to do is to say what is 215 in base 7 divided by 5. Okay, that's the first question. How do we do this? Okay, so what you need to do is to say it's doing the same thing. Let me see what the time is. Okay, we still got time. So I am going to start up something on the side and see if it is working here, because it's harder to do this using just a text editor. So I'm going to turn to my tablet and see if my tablet can do this. Oh, it doesn't look like it wants to do it. Darn it. Because I have to do a longhand division. I can emulate that. Oh, there we go. It does accept the invitation. Okay, so that's good. Alright, so that works. Excellent. Alright, so what you're seeing here is the screencast of a tablet. It's called Remarkable. You can look it up. And this allows me to do freehand writing and stuff like that, which is going to be handy in this case. So what we have here is 215, and it is in base 7 divided by 5, which is also going to be in base 7. Now 5 is just 5, okay? As long as you have a base that is at least 6, the digit 5 is always just representing the quantity of 5. So it's not a big deal. So we know that there's no 5 in 2, so we put a 0 here. So now we look at 21 as a base 7 number, and we ask, how many 5s do we have in 21 as a base 7 number? So without being very used to base 7, you kind of have to go through the base conversion first, okay? So 21 as a base 7 number is 2 times 7 plus 1, which is what we know as 15. So I'm going to put a 3 here, and it's going to be 21, and then we have a 5 left here, and then we have a 1. So the answer is it is a 3, 1 with a remainder of 0. So what this is telling me is D0 is going to be 0. So instead of using the formula that we have been talking about, what we can do now is to take this, this is called the quotient. So we'll take the quotient and divide it by 5 again. So this time we have 3, 1 in base 7, and then we divide that in return by 5. and see what we're going to have. There are no 5 in 3, so now we have 3 1 in base 7, and we want to find out how many 5s we have. So 3 times 7 is 21, 21 plus 1 is 22, so we are basically asking how many 5s we have in 22, what we know as 22 in base 10. There are 4 of them. So how do we write the value of 20 as a base 5 number? So we look at that as there are 3 5s, no, there are 4 5s and no 1s. Ooh, wait, hold on. No, this is in base 7, never mind. So it is in base 7, so we have 2 7, which makes up the 14, and then the 6, that is the remaining portion of the 20. And then now we have to do a subtraction in base 7 because everything is in base 7 here. So now we do a subtraction in base 7. And this is way ahead of time because we are going to look into the concept of borrowing and single digit subtraction and stuff like that. But I'm just going to skipping ahead and do this. So we look at 1 and we look at 6 and we go like, that's not enough, right? Because 1 is less than 6. So what we do is we're going to borrow. But in this case, when we borrow, we are not borrowing a 10, we are borrowing a quantity of 7. 7 plus 1 is 8. 8 minus 6 is a 2. So we have a remainder of 2 here. So that means D1 is going to be the remainder, which is a 2. And because the quotient is a 4, which is less than the base that we want to convert to, which is 5, so now we know that D2 is just 4. So according to this, 420 in base 5 should be representing the same value as 215 in base 7. Alright, so how do we check this? Because Tech can claim whatever he wants. So that's one thing that I would encourage all of you to do, is at least in your mind, ask that question. How do we verify that this is correct? Okay, after doing all these steps, and you seem to understand all of that, how do we make sure the answer is correct? So what we do is we look at this 0 and go like, there's 0 times 1. This is 2 times 5 because it's the quantity of 2 times 5 to the power of 1 in this case. So that would be a 10 in base 10. And then this is 4 times 5 to the power of 2. So 5 to the power of 2 is 25. 4 times 25 is 100. Right there. And these are all in base 10. Now we look at the base 7 number. The 5 is telling us that we have 5 times 7 to the power of 0, which is just really 5. And this one tells us we have 1 of 7 to the power of 1. And this one is telling us we have 2 of 7 to the power of 2. So this is 2 times 49, which is 98. So now we add up these numbers. 98 plus 7 is 105. 105 plus 5 is 110. And these also add up to 110. So I have just used what we have talked about today to double check and verify that the what we know as in base 10 as 110, 110 is 215 in base 7, and it is 420 in base 5. So hopefully that answered the earlier question of how you would convert between two bases without going through base 10. So this is how we do it without going through base 10, is to do basically we're trying to do division in other bases, and we're going to have, and implicitly we're also doing subtraction in other bases. All right, let me look at the time. All right, excellent. This is all getting recorded, okay? So remember, it is really important that you go back to review the content in the lecture and then use the review to update your notes. Okay, so because your note may have some question marks and go like, okay, I'm not quite getting this. This is blank at this point. So this is, when you review the notes, when you basically watch the video again, it's a good time to update your notes. Okay, basically you just add the additional understanding to your notes. Now, if something is still not understood, my suggestion is to go over the video slowly. Okay, now if there's a term that I refer to that you don't understand, you look up that term, and if that term is referring to some other term that you don't understand, then you have to quote unquote recursively look up those terms. Okay, because you have to look up those terms until you get to the point where you say, yep, I got this one. Okay, now can I back up one level to the next one that I did not quite understand? So that is how I would suggest people to study and to understand the content of a class. Alright, so I think we are running out of time, so it is time for me to release the lab at this point. So let me go to today's lab. It's a continuation of the other one that we did the other day. So I hope you have saved the file, but if you have not saved the file, I believe you can go back and retrieve the file from Canvas. It's NAN2. It's already released, but it does require a passcode. So this is when I release the passcode so that you guys can get started. Several things that are important. I do allow multiple attempts, and it keeps the highest score. Okay, but this time I turned off this feature. I turned off let students see their quiz responses. Incorrect questions will be marked in student feedback. So that means it will make it harder for people to use the trial and error approach to try to figure out the answer without understanding the material. It doesn't make it impossible. It's just a little bit harder. Just a little bit harder. The passcode is Nandroid. So I'm going to type it here. Nandroid is the passcode, and it is due at 1:20 p.m. So if you say, well, I'm really signed up for the second lab, which means, I can go off and take a break and then come back to continue with the lab, that's your choice. I mean, that's entirely up to you of how you want to allocate your time. I'm just saying that it is due at 1:20 p.m. So between now and 1:20 p.m., it is up to you to schedule your time and how you want to approach this. But I will be online. That's my obligation. Is I'll be online monitoring the text channel and also the direct messages on Discord, so that if you have any questions, hopefully I will have a way to direct you to find the answer. Yes, I did say I will find a way to direct you to find the answer. I did not say I will give you the answer straight away. So, with that said, are there any questions before we end today's screen share and live stream? All right, thank you. Implicitly, it seems like everybody is okay, at least for the time being, until they get to the lab. Very good. All right, cool. So I'm gonna turn off my voice channel right now, and then also stop streaming. I'll go get something to eat, just get a snack, and I'll be back by 10:30 at the latest to start to answer questions. So if I don't see you again, have a good rest of the day and have a good weekend, because we are not gonna see. I'm not gonna. Okay, you're not gonna see me until next Tuesday. So use the weekend wisely. Review the material. Review everything that we have gone through up to this point. Write your notes so that it's easy for you to locate the definition of stuff. Okay. And try to understand all of the concepts. Make sure that you are comfortable with the explanation, the examples, and so on. So that's just my advice, my suggestion.